All right, let's dive into the invisible world of chemistry. You might think it's all just chaos, but really, it's this incredible constant balancing act. It's called ionic equilibrium, and it's the secret sauce that keeps everything, from our own bodies to the vast oceans, amazingly stable. So how does it all work?
I mean, have you ever really thought about this? You can chug a soda, which is pretty acidic, right? But your blood doesn't suddenly become fatally acidic. How is that possible? Well, the answer is all in these super elegant chemical systems we're about to unpack. And this isn't just some textbook chemistry problem. This is literally a survival mechanism.
And that right there brings us to our first huge idea, this constant pH balancing act. Think about it. So many chemical environments, especially inside our own bodies, are constantly fighting to maintain a super specific, super stable pH level. Our blood is the perfect example of this. It has to stay in this incredibly narrow, razor-thin pH range right around 7.4 just to keep us alive. Any big swing either way and we're in big trouble. So what's the secret? It's a built-in defense system, the carbonic acid bicarbonate buffer. And its whole job is to constantly fight off any pH swings and keep us in that perfect balance.
Okay, so what is this amazing defense system? Well, this brings us to the real heroes of our story today. Buffers. You can think of them as the chemical guardians, the bodyguards, that protect a solution's pH.
So, what's the official definition? Well, a buffer is just a solution that can take a hit. It can absorb small amounts of an acid or a base without its pH going haywire. This resistance, this ability to not freak out, is kind of like its superpower. We call it buffer action, and trust me, it's absolutely crucial for tons of processes.
So how do you actually make one of these things? The recipe is surprisingly simple, really. It's just a two-part mixture. For an acidic buffer, you're going to pair a weak acid with its salt. And for a basic buffer, you guessed it, a weak base paired with its salt. That specific combination, the weak thing plus its salt, that's the whole secret ingredient right there.
Okay, so we know what they are, we know what they're made of, but how do they actually do it? How do they pull off this magic trick of stabilizing pH? Well, spoiler alert, it's not magic. It's just some really clever chemistry.
The whole secret boils down to this principle called the common ion effect. Here's how it works. A weak acid, doesn't really like to break apart or dissociate all the way in water. But then you add a salt that shares an ion with it, that's the common ion. What happens? It pushes the equilibrium or the balance back. It basically tells the acid, hey, don't break apart so much. It's exactly like chemical peer pressure, and it's what keeps the whole system in check.
Okay, let's see this in action. Imagine we throw a strong base, like an intruder, into our buffer solution. Immediately, the weak acid part of the buffer springs into action. It grabs that base, neutralizes it, and turns it into harmless water and a bit more of its partner salt. And the result? The pH barely even budges. It's amazing.
And it works the other way too. The same thing happens just in reverse. Let's say we add an acid this time. Now, the other half of the buffer, the base part that comes from the salt, it steps up to the plate. It soaks up that extra acid, turning it right back into the original weak acid. So once again, the pH stays stable. This buffer is basically always ready to defend against attacks from either side. It's a two-way street.
So this is all fantastic, right? But for chemists, just knowing how it works isn't enough. They need to be able to predict things, to actually design these systems from scratch. And luckily for us, there's a really powerful tool for that.
And here it is, the Henderson-Hasselbalch Equation. Yeah, it's a mouthful, but this beautiful little formula is the key to calculating the exact pH of any buffer. All you need are two things, the ratio of how much salt you have versus how much acid, and this one value called the pKa. And the pKa is just a number that tells you how strong that particular acid is. That's it.
All right, let's run through a quick example. Let's say we've got a buffer made with acetic acid and its salt, sodium acetate. We look up the pKa for acetic acid, and we see it's 4.74. Now, all we got to do is just plug that number and the concentrations of our salt and acid right into the equation. And boom, just like that, the math spits out our answer, 4.79. It's that easy. Using this one simple equation, we can predict and even design buffer solutions with incredible precision.
Okay, but buffers are just one piece of this whole equilibrium puzzle. It gets deeper. The very salts we use to make them can actually change a solution's pH all by themselves. And even solids, the ones that look like they barely dissolve at all, they also play a huge role in this delicate balancing act.
This is where something called salt hydrolysis comes in.
See, it turns out that when you dissolve certain salts in water, they don't just, sit there and chill out. Their ions can actually react with the water itself. And this process is basically the exact reverse of a neutralization reaction. And that reaction can end up producing extra acid or base, which of course changes the solution's pH.
And this table here breaks it all down perfectly. If you have a salt made from a strong acid and a strong base, think regular table salt, nothing really happens. The solution stays neutral at pH 7. But if your salt comes from a weak acid and a strong base, the solution's going to turn basic. And on the flip side, a salt from a strong acid and a weak base will make the solution acidic. It really all just depends on which parent, the acid or the base, was the stronger one.
So, what about those solids I mentioned, the ones that hardly seem to dissolve? Yep, we've got a tool for that too. It's called the solubility product, or KSP for short. The easiest way to think about KSP is as a hard limit. It's a specific number that tells you the absolute maximum amount of a solid that can dissolve in water before that solution is just completely full, completely saturated.
Now, to predict what's going to happen in a solution, we compare that KSP limit to something else called the ionic product, or IP. The difference between them is really simple, but it's super important. KSP is the fixed limit for a solution that's perfectly saturated, perfectly in balance. IP, on the other hand, is just a snapshot. It's the concentration of ions right now at any given moment.
And by comparing these two numbers, we can basically predict the future. It's simple. If your IP snapshot is bigger than the KSP limit, the solution is supersaturated, it's overfilled, and a solid is going to precipitate out. If your IP is less than KSP, then hey, more can still dissolve. And if they're exactly equal, the system is perfectly balanced right at the saturation point.
Okay, so we've talked about buffers, we've gone through salts, we've looked at solubility, we've seen the chemistry, we've even seen a little math. But now let's just take a step back and ask the most important question of all. Why does any of this actually matter?
Well, here's why. Because understanding all this equilibrium stuff isn't just some boring academic exercise. It literally gives us the power to predict and, more importantly, control chemical environments. It's the difference between just being at the mercy of random chemical reactions and being able to actually engineer them to do what we want.
And believe me, this has a massive impact on the real world. In medicine, it's all about keeping our blood pH stable and designing drugs that actually work properly. In the environment, it's absolutely crucial for things like monitoring ocean acidity and making sure our water is safe to drink. And in all kinds of industries, it's what ensures everything from the food you eat to the pills you take are stable and effective.
So these principles of balance, they are literally everywhere, almost always working silently in the background without us even noticing. Which kind of leaves you with one final thought, right? If this delicate, invisible dance of ions is what's keeping our blood, our oceans, and so many products stable, what other invisible equilibria are out there, constantly at work, balancing our world in ways we haven't even discovered yet?